folks, today we are doing electromagnetic induction. Now, let's consider these two cases. Now, let's consider our first case like we have a conductor, a wire that has been coiled around some sort of a hollow cylindrical object. Now, and then we have a bar magnet of a north and a south pole. Now, we try to initiate some sort of velocity towards the solenoid. Now, in fact, after coiling the wire around that particular object that is hollow to allow magnet to penetrate through, we connect the end of the conductor or the wire to an instrument we call the galvanometer, G for galvanometer. Now, the moment we draw the bar magnet towards this particular solenoid or inside the solenoid, the moment we draw it inside the solenoid, we realize that there will be a deflection in the galvanometer. That signifies that there has been an induced EMF and consequently an induced current. So it means that the pointer on the galvanometer will be deflected towards this direction. That is giving an impression that current has been induced. Now we want to know the direction of flow of the induced current. According to Lenz's law, anytime you initiate a bar magnet towards this particular solenoid, the solenoid assumes a magnetic field in order to oppose this particular magnetic flux. And for this reason, the solenoid assumes a north pole and a south pole. A north pole in order to repel that magnetic force. The north pole in order to repel that magnetic force that is, being initiated by the magnet. And for this reason, we would have to use Fleming right-hand rule to determine the direction of flow of current, of an induced current. We want to know the direction to which the induced current will flow, and that is when we use Fleming's right-hand rule, which says that whenever the thumb and the first two fingers of the right hand are stretched out such that they are all perpendicular to each other, and then we point a thumb in the direction of the motion of the conductor, then the first finger in the direction of the field, that is the magnetic field, then of course the second finger will be pointing towards the direction of the induced current. So for this particular, we have to put our thumb, we have to locate our thumb on the north pole of the magnetized solenoid, and then we coil our hand. When we coil our hand in, we'll realize our power, the induced current will be flowing towards this direction. So it means that current will be flowing this way. And that will cause the deflection in the galvanometer. Now let's consider our second case. In this case, you realize that we have reversed the velocity of the magnet. We have reversed the motion. This time around, we want to drag away, the bar magnet from the solenoid and observe the pointer on the galvanometer. We would realize that anytime we draw the bar magnet away from the solenoid, the pointer there will be a deflection in the galvanometer that indicates that current has been induced, and the pointer will be deflected towards this direction. Why? This is because when you drag away the bar magnet from the solenoid, it is believed that some sort of magnetic field or magnetic flux has been drawn from it, and for this reason this side would have to assume some sort of magnetic field, so a south pole and a north pole, so that the magnetic field that has been sort of drawn away by the bar magnet would be attracted back by the south pole of the solenoid, because unlike poles will attract, like poles will repel. So this side is signifying that the magnetic field that is sort of being dragged away will have to attracted back in order to nullify the effect of the magnetic flux by the bar magnet. And for this reason, this part of the solenoid assumes a south pole and this side assumes a north pole. And for this reason, the direction of flow of the induced current will be such that we use Fleming's right-hand rule and point our thumb on the north pole of the solenoid there, the magnetized solenoid, and then coil our hand inwards this way So it means that current will begin to flow towards this direction according to Fleming's right-hand rule. So that will cause the deflection in the galvanometer. So what is then electromagnetic induction? Electromagnetic induction is actually the generation of electric current as a result of a relative motion between a magnetic field and a solenoid, a magnetic field and a coil conductor. Alright, so if you are able to generate electric current as a result of a relative motion between a magnetic field and a coiled wire, then we are doing electromagnetic induction. And the current that is produced, or the current that is induced, is known as the induced current. So what is then an induced current? Induced current is the current generated as a result of a relative motion between a magnetic field and a coiled conductor. Alright. So in exam, when it asks you to define electromagnetic induction, you should be able to establish the fact that you should be able to tell the examiner that, this is only the electric current that is generated as a result of the relative motion between a magnetic field and a coiled conductor. Should we have this particular setup remaining stationary without the magnet being initiated, any movement, then there wouldn't be any, deflection on the galvanometer. So it means that for this, setup to yield any deflection in a galvanometer, there should be a relative motion. It's either the conductor is doing a motion while the magnet is stationary, or the conductor is stationary while the magnet does the motion, or both the conductor and the magnet are doing the relative motion. However, there has to be, in any case, there has to be a relative motion. All right. So, think of generators when we talk about electromagnetic induction. Generators that are used to power, generators that are used to convert mechanical energy into electrical energy use the principles of electromagnetic induction. And then hydroelectric power plants also use the principle of electromagnetic induction. All right, so before we move on, there's one particular factor that really need to be considered when you are talking about electromagnetic induction, and it is the only factor, or yes, it is the only factor that makes electromagnetic induction fruitful. And this factor I'm talking about is called the magnetic flux. Which has the symbol 5 with a subscript B. So what is a magnetic flux? Now let's consider a circular or a spherical, conductor. Should we have a conductor which has a surface area in the form of circle? So a circular, or a spherical current carrying conductor, which has a normal. Then we decide to place the magnet, which will give us a source of magnetic field, such that it produces an angle, say alpha, between the normal, and the magnetic field. Alright, so it means that we've been able to orient the bar magnet such that the magnetic field that it produces is subtending an angle to the normal of the coiled conductor. So it means that this will be the surface area of the conductor. Then, should we use vectors to resolve for magnetic flux, then we can say the magnetic flux will be equal to the product of the magnetic field, which is otherwise known as magnetic flux density, the area of the current carrying conductor, that is the area here, and then the cosine of the angle between the magnetic field and the normal. Alright. So it means that what can we see? We can see that the magnetic flux, which is produced by the magnet, the bar magnet, is dependent on the magnetic field. It is also dependent on the area of that is the surface area of the conductor, as well as the angle between the magnetic field and the normal of the conductor. Alright. Now let's consider, this means this will be our first case. I'll call it case 1. Let's consider our second case, case 2. Case 2, we still have our spherical conductor with a normal. But this time around, we have placed the bar magnet such that the magnetic field that it is producing is perpendicular to the normal of the conductor. It means that we've been able to position the bar magnet such that, the magnetic field that it is producing is perpendicular to the normal of the current conductor. So it means that this would be the surface area of the conductor, and this is perpendicular. Then what can we derive, from this? We can say that the magnetic flux will then be equal to the product of the magnetic field and the surface area of the conductor, and then the cosine of the angle between the magnetic field and the normal. However, the angle between them is perpendicular, and for this reason we can say alpha is 90 degrees. And cos 90 degrees is 0, means that should we position our magnetic field such that it is perpendicular to the normal, then means that our magnetic flux will be 0. So what can we write from here? You can write that the magnetic flux is minimum the magnetic flux is minimum when the magnetic field is perpendicular to the normal. So we should take note of this. In exam, when they ask you at which angle is the magnetic flux minimum, you should know it's at an angle of 90 degrees. So we could say the magnetic field has been placed parallel to the surface of the conductor. So when we hear the question, the magnetic field is parallel to the surface of the conductor, you should know that it's perpendicular to the normal. So it is 90 degrees. Note. Alright, so that is our second case. We should note this. Alright. Now in our second case, let's consider our very last case, that is case 3. In our very last case, we still have our spherical, conductor with a normal. This time around, we are trying to orient the magnetic field such that it is parallel, to the normal of the conductor. So the magnetic field has been placed such that it is normal to it is parallel to the normal of the conductor. It is parallel. So that is the magnetic, field. It has been oriented such that the relationship between the normal and the magnetic field has an angle of 0, because if two or more lines are parallel, that means that the angle between them is 0. So it means that we can say the magnetic flux for this particular situation will be equal to the product of the magnetic field, the area of, that is the area here, the area of the conductor, and the cosine of the angle between them. But at this time, the angle is 0 degrees, and cos 0 is 1. So it means that we can say the magnetic flux would remain only the product of the magnetic field and then the area of the conductor. So it means that the magnetic flux is maximum if you want to achieve a maximum magnetic flux, then the magnetic field should be positioned such that it will be parallel to the normal of the, the conductor. So magnetic flux is maximum when the magnetic field or the magnetic flux density is parallel to the normal. Alright. So this one, so let's take, examiners can twist the question. If the magnet is such that the magnetic field is perpendicular to the surface of the conductor, and it means that it's parallel to the normal. So we are always making it with respect to the normal. Should the examiner tell you that the magnetic flux, the magnetic field is perpendicular to the surface of the conductor, it means that the magnetic field is also parallel to the normal. Here too, if they say the magnetic field is perpendicular, to the normal, it means that it is parallel to the surface of the normal. So it's parallel to the surface of the conductor. Alright. So what can we infer from this? It means that if you want to achieve a maximum, magnetic flux, try to orient, the magnetic field or the conductor such that they will be parallel to each other. Alright, so it means that if you the magnitude of a magnetic flux is dependent on the orientation of the magnetic field with respect to the area, of the conductor. Alright, so in example, when they ask you to state some of the factors that influence the magnitude of a magnetic flux, you would say the orientation of the magnetic field with respect to the area of the conductor. You would say the magnetic flux density or the magnetic field. You would also say the surface area of the conductor. You can possibly say the angle between, the normal of the conductor and the magnetic field. Don't forget. So factors that influence the magnitude of a magnetic flux, we can talk about the orientation of the magnetic, field with respect to the normal of the conductor. Alright. You would also say the magnetic, you could also say the magnetic field. You would also say the surface area of the conductor and then the angle between the normal and the magnetic field. Alright. So I think at this juncture we've come a long way. So let's quickly look at Faraday's law of electromagnetic induction. So we are talking about Faraday's law. Faraday's law states that during electromagnetic induction, an EMF is induced, and this EMF induced is directly proportional to the rate of change of magnetic flux. Alright, so Faraday says that during electromagnetic, induction, an EMF is induced, and this induced EMF is directly proportional to the rate of change of magnetic flux. So the rate of change of magnetic flux means that the change of magnetic flux with respect to change in time. So this is what Faraday law states. The induced EMF during electromagnetic induction is equal to the change, or is directly proportional to the change of magnetic flux with respect to time. And then Lenz also came in and said that during electromagnetic induction, of course, let me give you the scenario one more time. Let's say this record the quality to maybe a galvanometer, the pointer G. You give it some sort of magnet and the south pole. Lenz's law about electromagnetic induction is saying that during electromagnetic induction, the direction of flow of an induced, EMF is always towards a direction as to oppose, the effect of the magnetic flux. So it means that if you are giving this, if you are drawing the bar magnet toward the solenoid would have to assume some sort of force in order to oppose that effect that you are giving it. And so the induced EMF during electromagnetic induction would have to move towards, a direction so as to oppose, the magnetic flux, causing a change in this particular setup. And so Lenz's law indicated a negative sign that sort of give an indication that in the direction of flow of the induced current is towards the opposite side of the rate of change of magnetic flux. So it means that Lenz's law came to obey Faraday's law and gave it a negative value. So that is what Lenz came to. So generally we can say that the induced EMF during electromagnetic induction will be equal to a certain negative constant change in magnetic flux with respect to change in time. But during electromagnetic induction, we have to factor the number of turns on the coil. Should we have a greater number of turns in a coil, it would give us, an increased induced EMF. Should we reduce the number of turns on a coil wire, we would have a reduced induced EMF. So for this reason, the constant of proportionality is going to be the N. So K is going to be the N, where N is equal to the number of turns on the wire or conductor. Alright, so it means that our induced EMF will have to be negative and changing magnetic flux with respect to changing time. But we know that magnetic flux is equal to the product of magnetic field, the area of, the conductor, and the cosine of the angle between the normal of the conductor and the magnetic field. So here our equation can be equal to negative and change in product of magnetic flux cosine of the angle between them divided by so it means that in exams, when they ask you to state some factors that influence or that would increase an induced current, you should also know that factors that would increase the induced EMF would be the same factors that will increase the induced current. So you should use this equation to solve for any problem that asks you to give out factors or suggestions that will help increase induced current. So realize that the induced EMF is dependent on a number of things. The number of turns, that is the number of turns on the coil wire. Should you increase the number of turns, you would increase the induced EMF. And then the B is the magnetic field. Should you increase the size of the magnet, you have increased the size of the magnetic field, you have increased the size of the magnetic flux density, and hence you have increased the magnitude of the induced EMF. Alright, should you increase the surface area of the conductor, you have somewhat increased the magnitude of the induced EMF. And then, the angle between them. And then should you also increase the speed at which, the rate at which you move the magnet to and fro, you would increase, the magnitude of the induced EMF. So factors that influence factors that increase. So factors that increase induced current. Let's say induced current or induced EMF. Factors that increase induced current or induced EMF. What can we say? 1. Surface area. Of the wire or the conductor. 2. Size of the magnet. So that will give us the magnetic field. And then we could also talk about the number of turns. The number of turns of the wire. 4. We can also talk about the speed of the movement of the magnet. And then 5. Do you have 5? Yes. The orientation, you can see the orientation of the, this is of the magnetic field with respect to the conductor, or of the conductor with respect to the magnetic field. This is the conductor. To the magnetic field. Alright, so in exams, if the examiner asks you to list some of the factors that will increase the induced current or the induced EMF, you should talk about the surface area of the wire or the conductor, the size of the magnet. You know, should you increase the size of the magnet, you are increasing the size of the magnetic field, and hence you are increasing the induced EMF or the induced current. Should you increase the number of turns on the wire, you have increased, you know, the induced EMF or the induced current. Should you speed up the movement of the magnet, you have also increased the induced EMF or induced current. And then if you are able to orient, you know, the conductor with respect to the magnetic field such that the angle between them is 0, that is, they are parallel to each other, you would have a maximum magnetic flux, and the maximum magnetic flux will lead to maximum induced EMF or induced current. All right. Thank you. So let's move on to how we are able to calculate the current that is generated during electromagnetic induction. All right. So that brings us to Ohm's law. When you look at Ohm's law says that voltage is, or the potential difference is equal to current times the resistance. But when you look at electromagnetic induction, in fact, the voltage or the potential difference is actually the induced EMF. So the induced EMF is actually the potential difference. which will be equal to the current times the resistor. So should you have the induced EMF, you can calculate for the current by dividing the induced EMF by the resistance. Alright, so this will be the equation that can be used to calculate for the entire current that has been generated. That is the induced current that has been generated as a result of electromagnetic induction. These are the formula. 1, 2, and then, I think we've come a long way. Thank you so much for sticking with me. I'll meet you, I'll see you in my, subsequent lessons where we look at some calculations involving electromagnetic induction and how we could use the formulae to solve IGC, physics questions. Thank you, and I would like to see you in my next video. Bye.